We, 4 of on-house group. Group of 10.
All right, we are ready whenever you are.
Getting very.
Okay.
Anytime. Yep.
Ready for the intro?
Yep.
Yeah, hi. It's my pleasure to introduce Spencer Hill. Spencer describes himself as a climate scientist interested in tropical overturning circulations, by which he means like monsoons, Hadley cells, and the ITCZ, and presumably also just more generic extreme rainfall. He got his PhD from Princeton University in 2016. And then he did a number of postdocs at Caltech, UCLA, and Columbia University. And it looked like he also had some affiliations with Princeton during that time period. And a year and a couple months ago, he started a position as an assistant professor at CUNY in New York City. And he still has projects collaborating with Columbia University on some of the stuff that he's going to tell us about, is my understanding. Yeah. Great. We're looking forward to his talk, and thanks to everybody for being here.
Good. Thank you, Larissa. Yeah, it's a pleasure to be here. Thank you all in person and online. This is the warmest room I've ever spoken in. Forgive my informality. Yeah, so before we dig right in, because it's confusing, those of you far from the 5 boroughs maybe don't care, but so the City College of New York, CCNY, is my university, and we are one of 25 colleges within the city university, the CUNY system, right? So Larissa was right that I'm CUNY, but it's like, you could be even more precise and say I'm at CCNY. Okay. I am always grateful for questions as we go. Please, you don't even have to raise your hand. Just shout them out. I would be grateful for that. Okay, so let's just start the stage, understanding what monsoons are in general. Then we'll dig into the Indian monsoon, why we might care about them, and then we'll dig into eventually the extreme rainfall and this ENSO story that we'll ultimately get into. Monsoons are large-scale, seasonally reversing, overturning circulations that are driven by the sun's own seasonality, right? So this sort of almost schematic style diagram for northern summer and southern summer, top and bottom. The orange is places where it's raining a lot by some metric. And you see in places like India, Southeast Asia, West Africa, you have in local summer, heavy rainfall, and in local winter, so southern hemisphere summer, you have dry conditions. And vice versa for the southern hemisphere monsoon zones as well. Here is the difference, northern summer minus winter, the 925 hectopascal winds. And for the Indian monsoon sector especially, as well the West African monsoon, you see this classic sort of cyclonic monsoonal near surface wind pattern. So these winds are bringing hot, moist air onto the continents and triggering a lot of rainfall. You can also think of them as each individual monsoon as the local manifestation of the sort of zonal mean or broader ITCZ Hadley cell complex, right? So this animation cycling through the months gives you precip at each location, and then this sort of schematic of the zonal mean overturning overlaid as the arrows. We see this strong zonal asymmetries, right? The individual monsoons, but also this very clear zonally symmetric component as well, right? In fact, most of my work has been about the zonal mean perspective, the ITCZ and Hadley cells, but this will be all about the very local Indian monsoon system specifically. Okay, so I'll be pretty brief on this introductory part. This was mostly slides for broader audiences, but why might we care about these systems and what's the sort of state of current understanding? The second part, we'll talk about seasonal mean rainfall, so it's average over the whole summer in India and the ENSO story there. And then the last part will be about daily extremes within Indian summer monsoon as a function of ENSO. Okay, so I'll summarize just at the jump our arguments of this sort of introductory part. The uncertainties regarding future changes in monsoon rainfall are very large, and we're just not going to straight compute our way out of them anytime soon. This is at the same time that they are really important historically, societally, and physically. And given that, we sort of advocate for a kitchen sink approach where there's this combination of theory, of modeling, and of observational analysis. Cribbing these ideas come from this 2019 review paper in Current Climate Change Reports, and then last year in Physics Today, a paper led by Michela Biasuti, myself, and Mick Fontaine. Okay, so the uncertainty part. A lot of my PhD work was on the West African monsoon, and so I'm borrowing from that region to illustrate this point. This figure here from a 2015 paper is a time series, so 1900 to 2100 on the X. You're talking like Sahel, so the African Sahel just south of the Sahara Desert, averaged rainfall over each rainy season, and model simulations. Each curve is a different CMIP5 model. And you see over the historical period, there's some spread, and then in the future, this is probably an 8.5, like very high, strongly forced scenario. You have a massive range of projections, right? Anything from very strong drying to even greater wetting, right? That was last model generation. The corresponding analyses from CMIP6, the more recent model generation, is that this actually only got worse, right? The spread is even bigger. So, you know, if you're a water manager in Niger, you're not going to be able to make many useful adaptation decisions with this kind of uncertainty, right? And yeah, the PhD work, a couple of papers, we looked at the mean sort of globally uniform component of warming, how that promotes dry advection into the Sahel from the Sahara Desert, if you're curious. Okay, so historically, arguably it was the monsoons that gave birth to the entire modern field of climate science. So Halley in the 17th century was basically trying to understand the trade winds and monsoons, you know, with these funny curvy S's that they used back in the day. And yeah, trying to understand these circulations, which they could infer from records of trading ships, etc. And El Niño Southern Oscillation, ENSO, also was discovered trying to understand parts of the monsoon, in this case, droughts in Indian summer monsoon. So Sir Gilbert Walker was with the British Meteorological Department in India, and he was trying to understand why there were strong monsoon seasons some years, poor ones in the others, and poring over the data, he ultimately found this relationship between sea level pressure anomalies in the East and West Pacific and the monsoon conditions. So he found the Southern Oscillation basically as part of that work. I actually, using this IMD, this rainfall data set I'll explain more later, I wanted to see, like, during his time, just how strong the signal would have been. So just going from 1900 to 1920, I'm showing time series of a sort of all India summer rainfall metric in the orange, and then minus Niño 3.4, the ENSO index in blue. And you can see what he found, right? So they were correlated pretty highly, about 0.6. Okay, so then societally, many millions, hundreds of millions, billions of people depend very intimately on the monsoon rains in India and beyond. So in 2010, the whole country of India, their finance minister, their department, secretary of the treasury in a sense, called the monsoon, the real finance minister. And you can see here this strong correlation between food production in India. This is this dashed orange time series from 1960 to 2020, and the blue curve, which is the all India rainfall index. It's not a perfect correlation, right? But in general, good rain, better crop yields, right? You can also see the red circles are El Niño summers, blues are La Niña summers, and there you see, right, red's mostly on the bottoms, and blue's mostly on the top. So in general, El Niño summers tend to bring drought to India as a whole, La Niñas tend to bring abnormally wet conditions. And this is, something like a large chunk of the whole population of the United States worth of people live in extreme poverty within India, and so are very strongly exposed to the conditions, the vagaries of the monsoon, right? Just very briefly on furthering this point, so the initial funding for this work came from the Indian Ministry of Earth Science, this monsoon mission extramural funding program. So the ministries in the Indian government are the equivalent of our departments, right? Department of State, Department of Energy, etc. And they have a Ministry of Earth Science. And Earth Science mostly is about the monsoon, right? So they have like a secretary of the monsoon, and a whole apparatus at that level. That's how important it is to the Indian welfare. Now we're going from the seasonal mean to the daily time scale. The extreme rain events there on daily time scales can be devastating. So all-time record in 2005 in Maharashtra Street, that's where Mumbai, the most populous city, is. Just outside of Mumbai, almost a full meter of rain fell in a single day, actually, in July of 2005. Which meteorologically is awesome, right? And was also devastating, right? Over 1,000 people were killed directly as a result. That's bad. On the positive side, the monsoon rain washes out air pollution very efficiently. So the left-hand side is from this really nice New York Times interactive they had a few years ago. This is from a single year in New Delhi, sort of central northern India, just seasonal cycle here, right? And it's PM 2.5 are the bars. And you see incredibly polluted conditions in the dry season, so everywhere outside of the monsoon. But then once the summer rains start coming in, it drops off precipitously, right? And then, in addition, this has inspired the monsoon complex is inspired all the way back to ancient literature of some really beautiful stuff. This is a classical Tamil poem that describes romantic love as this imagery of the rain mixing up with the red earth. Right? Yeah. First time I gave this talk, it was on Valentine's Day, so I felt like physically, monsoons, the time scale of variations of monsoons spans from sub-hourly to tens of millions of years. Here's, we can just skip over that, the millions of years part. On the tens of thousands of years time scale, right, a really fun problem is the Green Sahara. So about 8,000 years ago, the West African monsoon more or less extended all the way to the Mediterranean. And what is now the Sahara Desert was, if not forest, was grassland with many lakes and things like that. All right, last bit on this sort of introductory part. more technically, if you look into the zonal mean general circulation, right, the seasonally varying transports of momentum, of energy, of moisture, the monsoons are a leading order part of that story for Earth, right? So I would argue if you had to boil our entire general circulation down to the minimal possible ingredients, you would have the macroturbulent eddying extratropics, and you have the more zonally symmetric, steadier overturning in the tropics, and the Hadley cells, right? And the monsoons are just the seasonal manifestation of that, right? And of all the individual monsoons, India's is the strongest, the one that contributes most to that over all mass transport and other transport. So it's really important, okay? So you guys really should pay attention from here on out. Okay, so that's the intro. And now we'll dig into the seasonal mean rainfall problem. I left this sort of cheeky subtag here. The way we would summarize, one way of summarizing this work is just do the most obvious thing and just use your data. Be a little bit careful with what data you use. This work was published in 22 now in GRL. Adam Sobel, Michela Biasuti, and Mark Kane were my co-authors. Yeah, and they were my advisors as well for that postdoc at Lamont, from which all of this has grown. Okay, so the rainfall in India is highly, highly seasonal. So the way to illustrate that here is with data from Wikipedia about Mumbai monthly totals versus New York City, where I live. And you can see essentially zero seasonality in New York. Some of this is snow in the winter, right? But in terms of liquid equivalent, there's basically no seasonality. Whereas in Mumbai, there is almost zero rain for 7-8 months of the year, and then this massive spike peaking in July. Excuse me. You can see this using daily data as well, which this curve is. And as such, you can simply, it's useful, it's meaningful to create a rainy season average by just restricting to June through September, okay? So June, July, August, September. One exception is the far southeast, sort of peninsular India, is sort of this anti-Goldilocks zone where it just misses the summer rain-bearing disturbances, and it actually gets its rainy season in the autumn through the retreating northeast monsoon, it's called. The monsoon sort of retreating back and clips it on the way back down. The data set we're going to be using for the rest of the work here is from the IMD, the Indian Meteorological Department. This is a quarter by quarter degree gridded daily product, and crucially it goes all the way back to 1901. So British colonialism, Walker, for all of its horrors, a upside for us as scientists was that they kept very meticulous weather records. They established a station of thousands of networks. You can see them depicted here. And so having this high density of station data going back to the 19th century is pretty much unparalleled. Yeah?
How did that, that's very dense, how did that vary over time? What was the sampling?
Yeah. In space, I couldn't tell you. In terms of total count, it's like, it varies from a couple thousand or maybe less early on, and then a peak, I think in the 80s or so, of 4,000 or 5,000 or something like that, and then decreases again. And it is worth noting this data set, it includes sort of all the data available at any given time. So there is, when it comes to looking at trends especially, there is a major concern about the aliasing of the network changing. There's at least one nice paper about that I'm familiar with. For our work that's about interannual variability, it's not as much of a concern. And the IMD also produces a 1 by 1 degree product where it's not just a coarse inversion, it's a fixed station network. and all of the results are hold in either case. Okay, so yeah, so this is the data set we'll use, and then we'll just use good old Niño 3.4 to characterize ENSO, and we'll use fields from era 5 to look at the large-scale environment. Then you're restricted to the satellite era, so post-79. Okay, so I'm showing here, you take this daily rainfall, you average it over the full 122 days of summer, and you average that over all 120 years, and you get this plot of just summer mean climatological rainfall. And you see this very strong spatial heterogeneity, right? So the monsoon it's a very wet region, but zooming in, you see this very rich spatial structure, strongest in this narrow coastal band in the southwest. Next, sort of another hotspot in central India here, and then very high as well in northeast India near Bangladesh. However, we are going to mask out that whole northeast region as well as the Himalayan foothills because of just data quality issues. There's not enough stations in the Himalayas, and there's lots of bad data that messes things up if you don't omit it up here near Bangladesh. So that's just a technical point. Yeah, I'm going to skip over. This is just an example of one of the clearly errant time series or individual grid points. It's just, yeah. Don't look at the northeast. This is what we're going to do. Okay, so you take any particular year, 1995 is shown, and you simply average that over the whole domain, all of the grid points, and you call that your All India Rainfall Index, or ARI. It's just the mean rainfall for that season, for that year, for that, yeah. And this is a very widely used metric of the total monsoon sort of behavior. And you can create just an annually resolved time series from that procedure, right? That's this curve here. So it's a very popular target for like evaluating model performance. It's they try to seasonally forecast the ARI value, but it's also been questioned for now decades if it's truly physically meaningful and sort of societally meaningful as well. So Sulochana Gadgil is a great Indian scientist. She helped us out a lot on this project actually. But back in 1995, her argument was that this index is not very meaningful on the basis that you don't have homogeneous anomalies of rain over the whole subcontinent. So some places are dry, some places are wet compared to the average in a given year. And so this average over those different parts is therefore somehow not, you're doing too much averaging. And then others have argued that, well, it's not the amount of rainfall in total that matters, it's how spatially extensive drought is, right? So if your rainfall is very heterogeneous the way it is, the total amount of rainfall versus the total coverage of drought could be, in principle, could be very different quantities, right? And to this day, mailing list flame wars, the battle wages on all this stuff. Yeah, again, just highlighting that indeed the rain falls unevenly in space. So again, looking at the climatology. I think I said almost all of this already, but just to put some actual numbers on this, in much of the southwestern coastal band, you're talking about 2 meters of rain falling climatologically in a 4-month span, right? So on average, every summer in 4 months, you're getting 2 meters of rain. I mentioned already that coastal band and this sort of broad elevated region called the central monsoon zone, central India. Conversely, it's much drier in the southeast, which I alluded to, and it's also drier in the northwest, sort of as you get to Pakistan. All right, why does that, how to think of these physically? For the southwestern coastal band, it's mostly topographic, right? So you recall that monsoonal circulation coming from the southwest, and you have this kilometer to 2 kilometer peaks right along the coast. And so it's just very directly this really steady onflow, and they have to rise over the mountains, and so it just dumps rain all summer long. For this central Indian sort of next hotspot, there it's more of a synoptic story. So we have forming in the Bay of Bengal, several every year are called low pressure systems. Oh no, he was technically out of Michigan. You guys had a guest student for many years, Hao-Chun Luo, who's now working with me as a postdoc. His thesis, he came here from Michigan with Angel. His thesis was about these low pressure systems. Anyhow, these form over the bay, and they propagate west-northwest over the subcontinent, and they are responsible for a large fraction of the heavy rain in the summer, especially over the central India region. So the southeast is sort of this, like, it gets the orographic rain shadow from the Ghats, and it just happens to not be in the track of many of these low pressure systems. It's just a little bit too far south from them. So that's how to think about the spatial structure of rain to first order. Okay, so we can make an alternative to the ARI, the All India Rainfall Average, which is just counting how much of the domain was anomalously wet versus anomalously dry. That's shown here. So in 95, for the example, count up the number of grid points where it was anomalously wet. That's the metric. And you do that for every year. This is getting to whether the total rainfall and the spatial extent are going together or not. That's the motivation. And the point is that yes, they are. So the correlation between the two is 0.96. And it's that simple, right? So I think this was kind of a big nothing burger where people were saying, you know, in principle, the ARI isn't telling you about the spatial extent, but if you just look at the spatial extent, it is indeed telling you that. Okay.
So how come nobody did this before you guys?
Yeah, it's a good question. We were talking about before that. So the Indian research community they do a lot of great work on the monsoon, but they tend to be there are sort of particular ways of thinking about the system and types of analyses that groups sort of just latch onto, and just that's how you attack the problem, and there's not very much deviating from those specific angles, and this is not in one of those tracks, I guess, is one way of thinking about it. And then on the non-India side, I don't know. Yeah. Okay, so mechanistically, how to think about this tight correspondence? To try to get a little bit into that and segue into the extremes part, you can decompose the summer mean rain into a product of the number of rainy days, right? So days with non-zero rainfall in the blue parts, and the rain intensity, so conditioned on rain occurring, how much rain falls. I think that's pretty straightforward. Here's the climatology of that decomposition. So again, the total rain is the product of the number of rainy days. So in the southwest, it's raining almost every day. And the mean rain rate on rainy days. So in the southwest, it's raining almost every day and a lot. So you can create indices or investigate this rainy day rain intensity decomposition across years. Again, these slides are mostly for a broader audience, so some of it's a little bit pedagogical, maybe pedantic, depending on your interpretation. Okay, and the punchline is that ENSO brings drought through reduced number of rainy days throughout the region. The left is correlation coefficients point-wise between the total summer rain against the lag 0 Niño 3.4 conditions. And the right is the same, but just for the number of rainy days. In both cases, you have this pretty spatially, especially for the number of rainy days, this pretty spatially coherent, strong drying signal. Right, so the stronger El Nino is, the more of a drying influence it's going to give, and that will win out over an increasing number of grid points compared to other factors, non-ENSO related. And you can physically understand that pretty simply. This is domain mean, so all India mean profiles, ENSO composites, relative humidity on the left, so pressure is the y-axis, and vertical velocity omega in the right. And so you have a drier troposphere, and you have anomalous subsidence throughout the troposphere, El Nino versus La Nina years. Okay, so now we're starting to get into the segue into the extremes. I showed you the Niño relationship with mean rain and the rainy day frequency. Here now on the left is rain intensity. So on days that it's raining, how much does it rain? And now we see a very different story, right? So we have blues over much of the sort of central monsoon zone, meaning positive, meaning you're getting more intense rainfall in El Nino compared to La Nina years. And you see that sort of matches the first EOF when you look at this rain intensity metric as well. I think for the sake of time, I'll skip this, and we'll turn to the daily extremes part. I was feeling cheeky, I guess, and the tagline in this case was, we kept thinking that we were going to find the paper that had already done these analyses, and then we kept not finding it. This work included 3 others. So Destiny Zamir Myers was an undergrad at Columbia who did the original analysis that led to this sort of counterintuitive result with the extremes. Fayez Ahmed is, we'll see, we use his convective buoyancy metric, on which Angel, who could not be here, was a co-author, and then Mike Tippett helped us a lot with the statistics. A little background before going into the ENSO story. There's been a ton of research on trends, both observed and projected in extremes in India, like virtually everywhere. This is a famous paper about that in Science in 2006. And there is some credible arguments for positive trends in extreme rainfall in the region, but this is the paper I was mentioning to your question. That's also been challenged because of this changing network issue. It also, the extremes more or less unambiguously go up in future projections as well. So this is from a paper looking at CMEP6, very high emissions scenario, future changes in heavy rainfall, think of them as extremes. It's all blues, meaning they're all expected to become more frequent in the future, and especially along the sort of in the wet regions, right? So the central zone and the southwestern band. Our sort of argument is that there's this gap. You could think of this sort of 2x2 matrix, right? So secular trends on the one hand versus interannual variability, ENSO on the other. And with respect to the rain itself, looking at the seasonal mean or looking at daily extremes. And all of the quadrants except the interannual story and daily extremes are very well studied, but we just haven't found yet. It's taking forever to publish, so we might get scooped after all. But yeah, we just haven't found a good analysis of this problem. Maybe that's just because it's a boring problem and so no one wants to do it, but I think it's meaningful for 2 main reasons. One is even if our emissions go to 0 tomorrow, God willing, there will be ENSO, right? And so it's important to understand and ideally predict ENSO generated fluctuations in extremes. And as I hopefully have time at the very end, we have some initial hint of potential predictability because of the ENSO forcing of the daily extremes. Okay, the metric we're using is called the cutoff. This is from our literature spearheaded by Dave Nealon. It's essentially the transition point in the daily rainfall PDF. So I'm showing you a daily rainfall PDF in log space, and you have this sort of classic gamma-like distribution where you have this quasi constant slope power law range from low to moderate rainfall, and then this exponential decay in probability as you get to very heavy rainfall. And the cutoff is the point at which those separate from one another. So it's sort of like this integral metric of the whole right tail of the distribution. That's our main metric. We've checked everything against all of the standard metrics, exceedance counts, single daily max, et cetera, et cetera. It all checks out. All right, this is the big, maybe the single biggest take-home slide here is about the extremes. The left-hand panel is the climatology of this cutoff metric of the extremes. And you can see it's large in the southwest, as we expected, relatively large in most of the central monsoon zone. It's especially so in the west, and dry in the southeast. This, in the right-hand panel, is the correlation against Niño 3.4 of this annual cutoff, this extreme measure, against Niño 3.4, if I didn't say that right. Blues, again, means increase with El Niño, more extreme rain in El Niño summers, brown the reverse. And so, very similar to that rainfall intensity picture, now much of the domain, and especially the wet parts, right, the southwest and central India, El Niño summers bring you more daily extreme rainfall, even while they're reducing the seasonal mean and the number of rainy days. We did bootstrapping to do the statistical significance between that and the different data sets and the different metrics. We feel pretty confident that this isn't just an artifact of any particular methodology. I'm showing this sort of on a region aggregated basis on the right. So these four regions, AMI, the whole domain, the central monsoon zone, Western Ghats is the southwest, and then the last one is the southeast. It's all a similar story for the whole domain and the two wet subregions. The reds, the El Niño composites, are higher than the blues, the La Niña composites, and vice versa for the southeast. So that's just aggregating to a sort of more regional scale from the grid point basis. I'll skip that. This is just showing all the different metrics. Again, the results are very robust to the particular metric we're using. Here now we're looking as a function of return period or percentile of rain using what's called a risk ratio. So you take the ratio of the probability of exceeding a given percentile, say 20 percentile here, the probability of exceeding that in an El Niño summer divided by the corresponding probability for a La Niña summer. So if it's greater than 1, it's more likely in El Niños, less than 1, vice versa. And what do you see? The left panel, all of the regions, so each one of the curves is for a different of these four subregions. All of them are suppressed at the low to moderate percentiles, and in the dry southeast that continues through the whole distribution. But in the wet regions, the CMZ, the green, the Western Ghats, and the full domain in the black, you get this sharp uptick at the high percentiles. The right panel is just doing a log spacing, so to focus in on the extremes. And you get, for example, at the 99.99th percentile of rainfall intensity, for the domain as a whole, it's like a 40 to 50% increase. And for the Western Ghats, it's like a 70% increase in likelihood. Okay, why is that happening? To understand that, we're going to use this convective buoyancy metric from Vaez's paper in 2020 that I mentioned Angel as a co-author on. And this is using data from ERA 5. It's a local sort of point-wise metric. And it includes two factors. You have sort of your standard undilute buoyancy. So you take all the vertical variation just becomes two layers, a boundary layer and a lower free tropospheric layer. You define the undilute component of the buoyancy as just that of the subcloud layer relative to the lower free troposphere. But then there's also a subsaturation term, so how moist the lower free troposphere layer is, because entrainment of drier air will suppress convection as it ascends. And their real insight was that you get these really strong relationships. So these are rainfall conditioned for the different regions on this buoyancy metric. And you see, basically, until you approach neutral buoyancy in this metric, you get no precip, and then it picks up very sharply for each region. Right? Their paper showed that for other regions in different data. This is from our paper showing that it works for India as well in the summer monsoon.
And what are the dotted lines?
Those are the PDFs of the buoyancy itself. So that's this second axis. And so the nice secondary point there is that at this point, once the rainfall picks up, it rapidly consumes the buoyancy, right? Okay, so yeah, so it's a strong control, this B sub L metric on on rainfall throughout the Indian summer monsoon. And it's also to first order ENSO independent, this conditional rainfall buoyancy relationship. Now I'm showing just for that all monsoonal India domain, now conditional quantiles of rainfall, so a 10th percentile all the way up to the 99th percentile for a given convective buoyancy value. And I've overlaid in the red, gray, and blue, restricting to El Niños, all years, or La Niñas. And if they're hard to see over one another, that's sort of the point, right? So for each quantile, the same relationship between the buoyancy and the rainfall holds, whether it's El Niño or La Niña. So then that makes it easier, because then we can just say, well, what is the buoyancy itself doing under ENSO, right, to tell us what the rainfall will do in response.
Wait, sorry, what are the quantiles or quantiles of what?
Of rainfall for that given bin of buoyancy. So
there's like 10 curves and
yeah.
10 or 8
so
curves.
like the conditional mean is straightforward, right? You just condition on the buoyancy.
Yeah.
It's like this is the conditional median. This is the conditional 25th percentile.
Oh, I see. Okay. Yeah.
Yeah, that didn't roll off the tongue so clearly. Thank you for clarifying.
Yeah, so it's telling you about the spread.
Mm-hmm. But the bigger point is, yeah, so there's a huge spread, but the bigger point is that it's mostly ENSO independent.
Mm-hmm.
Okay. The things in the southwestern band are a little bit, we'll basically circle back to them. Otherwise, there is relatively good correspondence between the behavior of this buoyancy on the right tail and the rainfall signals. So again, blues means this is the full buoyancy metric and a 99th percentile value against ENSO. So blue means goes up in El Niño summers, brown the opposite. And you can see over much of the core monsoon zone, it goes up, so that checks out. And over the southeast and the northwest, it goes down, so that checks out. It's not perfect, it's more negative overall, right? But it's, we think, a useful starting place. Now we look at the individual contributions of the subsaturation, the moisture term here, and the undilute instability term on the far right. They mostly go together, right?
So this is just the, sorry,
Yeah.
where on that graph is this the buoyancy? It's
this
not
is,
like the mean, right? It's,
that's right. This is the, so we take a 99th percentile
this
across.
is the 99th percentile of the buoyancy. Okay.
Yeah.
Yeah, sorry, I missed that.
No. Right, so both over most of the domain, both the instability and the free tropospheric dryness are contributing to that same signal.
Mm-hmm.
I'll skip this. This is just, again, showing it on a region aggregated basis. Okay, So now we're sort of, that's the results as they stand, and now it's a little bit more speculative, interpreting, okay, well, why is the buoyancy then doing that, right? We sort of just kicked the can down the road. Again, except for the southwest, a slide or two that will come, we're thinking this is actually, the buoyancy is sort of the tail, not the dog, that instead it's this synoptic scale reorganization that's occurring. So these low pressure systems, basically it seems like they are shifting to further northward tracks and also less westward tracks into the northwest. This is ongoing work with Yu is leading this one along with Michaela and Ming Fong. The black contours here is the climatology of low pressure system track density. The shading is a composite El Nino minus La Nina of that density. And so you see the greens and blues mean more in El Nino summers and the browns less. And then the circles are the associated rainfall with the associated extreme rainfall with those systems by some metric of hers that I don't understand.
It's the size of the dots.
Yeah, I think it's how, I forget if it's how significant or how the magnitude. Yeah. I wouldn't have plotted it this way, but anyhow, if you compare this again to this map of the full buoyancy, I think you could agree there's pretty decent correspondence, right? So these systems are very moist in their core, and they bring heavy rain, and they're relatively unstable, and so it checks out.
Is there an advantage to looking at buoyancy versus just moisture? Is the buoyancy adding something to the story, or?
Moisture in terms of like column water vapor? Or?
Yeah.
We haven't, I don't think we've done the analyses. I think I looked at column water vapor. I mean, what Fayez's paper's argument was that it's a sharper, it's a more well-defined sort of uptick, right, rather than the gradual exponential with column water vapor.
Mm-hmm.
And so yeah, that would be the first thought. I keep previewing it. I'll talk about the southwestern band in a second, where we do think it's this undilute part of the instability
Okay.
that matters. So, yeah, those would be my two immediate thoughts. Yeah. So then, next question: what if you take this? If you buy this so far, why are the tracks changing this way with ENSO? And there we don't know yet. We're suggestions, ideas, welcome. That's not what Hao-Chun is working on. He's working on something totally different. Okay, finally, what's going on in the southwest? So this now is just the undilute instability component, and it's the, again, a positive, the blues mean you get more high instability days with El Nino, and you see, and this is the only place where it differs from the moisture part, you get this strong uptick within the coastal band here. And so our speculation is sort of skipping over the synoptic scale entirely. So you have this domain-wide, this steady subsidence and this anomalous dryness, right? Including in that coastal band. That's going to suppress your weaker convection events, more dry days as a result. And basically, convection, what it does is releases instability, right? And so if you have the weaker events suppressed, you're going to enable occasionally very high buoyancy values to build up until some passing advective event or wave then erodes the cap, and then something really intense is able to fire off. How exactly to quantify that is something we haven't settled on, so any thoughts there, I'd also be grateful for. Okay, so that's it for results. So just recap the main points, and then just one slide of sort of takeaways. Monsoons are important, and there's a lot more to learn about them. The season mean signal of El Nino on India summer monsoon is strongly promoting drought conditions, and that's mostly coming from the number of raining days going down. But you get this sort of strongly heterogeneous pattern in the rainfall intensity when it does rain. And if you dig into that part more carefully, you find that you get an increase in daily rainfall occurrence within the wettest parts of the domain via partly in the southwest, this buildup of instability, we think, and partly this synoptic low pressure story in the rest of the domain. Okay, very last thing I'll share is the seasonal predictability part. So what I'm showing on the left is the same correlation coefficients against Niño 3.4 of the cutoff rainfall metric as I showed before. So that data you've all seen before. The middle panel is using a forecast of the JJS Niño 3.4 from the North American multi-model ensemble, the seasonal forecast ensemble, initialized on May 1st. So this seasonal dynamical forecast ensemble can forecast the JJS value at about the R like 0.85 or something like that. So it's pretty skillful at predicting the summer ENSO state. And so when you use that in place of the actual value, so you've gained a month of information, right? Or you're a month ahead of things, the signal still looks mostly intact, right? And so I don't want to overstate this, right? The correlation coefficients here are, even when statistical significant, they're modest, right? They were below 0.5 in every grid point. So I don't know that this will eventually lead to actually useful predictability in the system, but at least raises the specter, if that makes sense. And yeah, I think with that I'll stop. Okay, thank you.
So we usually ask for the whether there are any student questions first. So any student questions?
Yeah, Roger.
So very interesting talk, Spencer. I'm just curious, I don't study only monsoon, I'm just curious about other climate variability index across Indian Ocean, which might also be affecting these processes or might be correlating with ENSO, like IOD or
Sure.
MJO. Can you tell how that could be teased out or tested about what is contributing to these things?
Yeah. Yeah, other variability modes. So the IOD, the nice thing about this framework, what we're sort of hoping to build this out into not just a one-off project here, is that it's all, you could swap in any other index, right? IOD, for example. No concrete results yet, though. This work originally, Solution Agile I mentioned, like, she was really pushing us to look at this, what she thinks of as the atmospheric counterpart to the IOD, called equinu. So sort of like the southern oscillation to El Niño, La Niña. And we just ultimately concluded that that was not real. So that's that side. But the IOD, that could be something. Yeah, you could do NAO. Folks have made arguments about North Atlantic teleconnections. And yeah, some of the, once you get to this seasonal mean decomposition, you have to do something different once you get to subseasonal behavior like the MJO. But yeah, we'd like to definitely think about that part of the subseasonal story too, not just the synoptic low pressure systems, but yeah, MJO type interseasonal stuff. Yeah. Go ahead.
Just have a very general question. So you said the Indian monsoon is the strongest. Why is it the strongest compared to other ones?
Why is it the strongest? Yeah, good question. A real key factor is the Himalayas, shielding that region from the colder, drier, extratropical air, right? So historically there's been a big emphasis on the whole Tibetan plateau and this idea, a thing called an elevated heat pump. Don't worry about that. What really matters is just the physical barrier of the mountains themselves. So basically, the monsoon, the sun's peak insolation in summer is actually at the North Pole, right? So the sun is most strongly insulating all the way deep into the extratropics, and the monsoons are trying, like, that pushes them to go deep, as deep as they can basically, but most of the rest of the domain, you just get this cold extratropical stuff that mixes in and sort of, the Sahara Desert does it for the West African monsoon, right? The very dry, there's an albedo part too, but forget that part. The point is the mountains block that cold air basically, and so then the monsoon can grow even further in extent, and as it does so, it strengthens in its overturning as well. Did that answer your question?
Yes. So, enjoyed your talk. As I was going through, when you're looking at particularly your response to the frequency of intense precipitation, it would seem to me that that southwestern part is mostly just orographic lifting, but you're saying that you think you're suppressing convection until you get really deep convection?
Yeah, so I mean, I think both can be true, right? So, Quentin Nicholas, he just finished his PhD with Bill Boos at Berkeley. They have his thesis work is a couple of papers out now that's doing this sort of very clean theoretical framework for orographic precip in the tropics. And it turns out that it's not as simple as the extratropical sort of just straight mechanical lifting.
Okay.
That it's actually sort of more, I'm going to botch the details, but there's sort of a more involved causality that involves the static stability responding, et cetera. And so, it's raining there, and it's orographically forced a lot, but it's not always, right? And it's that there's variability in there that, that's salient.
So you have a fairly long record of geostationary satellite data over there. Have you thought about looking, at, the overshooting tops or, the brightness temperature anomalies so that you could maybe look at that from a process kind of study?
Yeah. It's a good idea. Yeah. How far back would those go? Rough ballpark.
I'm sure you've got, I suspect you have 15 years?
15 years. Yeah.
I don't
Yeah,
really
with
know.
respect to teasing out the mechanisms,
Yeah.
you might, the statistics on all this would be
I think you probably get a couple answers.
a couple cycles, right? Yeah. That's not, it's a good idea. Quinn.
So we had talked a little bit at lunch about how the buoyancy varies, the drying buoyancy, the subsaturation buoyancy metric varies between reanalysis and other observations.
Right.
I guess I was wondering if, well, first this is from this is gridded from the observational data set, right? What you're showing.
The
there.
rainfall is this interpolation from the stations to the
Okay.
grid, and then the meteorological fields are ERA 5, and they happen to be on the exact same quarter-degree
Okay.
grid.
I guess I was just curious if you had looked at it in reanalysis and if you saw any sort of, I guess it's not really that relevant to what you're doing, but I'd be curious with what I'm seeing, if you see any major differences in when you look at it from the analysis and,
We haven't looked at the reanalysis rainfall, if that's what you're talking about. Yeah, I would be more sort of, in part from talking to Larissa and you about your stuff, I would be more almost interested in the reverse, which is looking at the, verifying the reanalysis fields, right?
That makes sense.
Against the station data. Yeah. I have an undergrad who just started working with me. She's using this IGRA radio sound database. I don't recall though how much of it's over that region, but that could be one way of doing it.
I looked at it a little bit this summer, and we had some hard times. We had a hard time getting temporal, especially temporal coverage of a lot of the radio sound locations. But
Oh,
I
okay.
didn't spend a whole lot of time looking at it, so.
Yeah. Yeah, that's just a fair point too.
Yeah, generally you don't want to use reanalysis rainfall.
Yes.
I was just curious if. Yeah.
Yeah, but that's.
Because the budgets don't close.
Go ahead.
Cool talk. I haven't thought about the monsoon in a while. So apologies if this is totally off base and I'm not remembering the figures from the talk. Often people use interannual variability as a stand-in for trends. Could you use this kind of interannual variability for extreme rainfall as a proxy for what could happen? Or are there reasons why the dynamic shifting of the storms in this case don't make that a good proxy for
Yeah.
global warming?
It's a great question, and thank you very much for bringing it up. So like,
You at the beginning and I don't remember.
no, it's all good. So I was telling Arissa, we're playing the tabloids game. We went to nature. We went to nature geoscience. Now we're about to go to science. And one of the unfortunate reviews was someone who said, well, Goswami showed that with warming, you're getting an increasing trend. So ENSO's warm, El Niño's warm, so what's this? There's no story, right? Like, this has been done. But I just don't, in general, the idea of an ENSO analog is, that's great, right? And when it works, that's great. But I just don't think it applies here, right? So their argument and the arguments about the projections are about just mean moistening, right? Sort of Clausius-Clapeyron, relative humidity, relatively fixed. And that mean moistening, whatever it does to the right tail for the extremes, don't think about it too hard, more extremes, And that's exactly the opposite of what's happening in the ENSO signal we see, right? So in the ENSO signal, this isn't ours, but just so that we have a map, right? It's this, the whole domain is drying, right? The whole troposphere is drying in absolute and relative humidity terms. And over here, it's this like right tail instability days thing we think is going on. And over here, it's this change in the synoptic tracks, right? It's not obvious to me at all that those tracks are going to change the same way under global warming, right? Or that would give rise, the same dynamics would be at play in the Southwest. So like we were really hoping that would be the case, right? But we talked ourselves out of it basically.
Yeah, 'cause people use it all the time as like an immersion constraint. But
Exactly. Yeah, that's what we were hoping.
Sure.
Yeah, exactly. It was like, there's your nature paper, right? Yeah.
Okay, well, we're over time, so let's thank Spencer.